And here we will just shortly revise and then focus on different applications. Before beginning, so let me once again tell you that you are recommended to use the lecture notebook here. Please do not rewrite what you have written in another book. Rough notebooks are required. And other thing, from the next time on, randomly, at the end of the lecture, I'll choose 3 groups, for example, to sit for tests on the previous topic. So randomly, I will choose groups for having tests, for having enough activity throughout the semester. So now let us now begin. Since we are going to explain fluids, since I'm not sure how much I am heard here, that's why I'll be close to the computer. Since now we will discuss fluids, we need to know what is fluid, this term. It is a collective term, and it denotes both liquids and gases. There are 3 states of matter, you know this, that's why I will not explain in detail. So solid state, liquid state, and gaseous state, each state having specific characteristics. Since fluids is the subject of discussion, that's why we will proceed with liquid state, liquids and gases, being both being fluids, liquids. So what are the main characteristics given in the slide? What is important here that they are characterized by the so-called short-range odor. So there is some odor, but with distance, so the odor is transformed into this odor. So they do not have their own shape, occupy the shape of the container in which they are placed. Another important characteristics being their incompressibility, which means that they cannot occupy smaller volumes unless enormous pressures are exerted here. But as we'll study in future, in liquids, both kinetic and potential energy exist or can be defined in contrast to gaseous state, in which there's almost no interaction between molecules, and the only interaction is in the form of collisions. That's why when we are discussing gases, we will consider just their kinetic energy, since potential energy is negligible. So, main concept in physics and in this topic as well is that of pressure. So, what is pressure? Shortly, mathematical definition given here in this blue shade. So what is given? Force divided by area. So let me pay attention, focus your attention on the force. So the force must be perpendicularly applied on the area. And in physics, there is a specific term which is called normal force. Force which is perpendicular to is also called normal force. That's why verbal definition of pressure is normal force per, we discussed this previous time, instead of divided by, we say per unit area. Why per unit area? Because if the denominator is 1, then pressure would be exactly equal to the force. So that pressure would be equal to the force only if the area is 1 square meters, for example. So that's why normal force per unit area. And what else is important here to mention? That pressure is a scalar quantity. Scalar, not vector. There is a vector in the formula, force, but it is scalar quantity since it is transmitted according to the Pascal's principle, which we'll discuss today, to every part in fluids, so in all possible directions. So, example, some medical application of pressure is the function of hypodermic needle. So it has exceptionally small cross-sectional area, which means that the denominator is small, which makes the ratio big, which means that via this small area, not so big force can produce large enough pressure for being, for functioning, for penetration. So given here in red, the same thing. So here, what is given in this slide? Since we discussed what is pressure in general, but there are different kinds of pressure. We've got molecular pressure, we've got hydrostatic pressure, we've got atmospheric pressure, so different kinds. And in this case, the so-called hydrostatic pressure is given, but to explain it, hydrostatic pressure is pressure due to the weight of some liquid or fluid column. Due to the weight. That's why P from pressure, H from hydrostatic, rho, so previous time we mentioned this is the Greek letter which we use for denoting density, then acceleration of gravity, which is a constant, and height or depth, depending on the specific situation. So let me show you in what way to derive this formula. It comes from where. So for that purpose, so let me switch on the board and take a container in the form of a cylinder, for example, so cylindrical container. And suppose it is filled with some fluid. So the fluid has got weight. Weight is a force. Weight is defined as the mass times acceleration of gravity. So since this is acceleration, so in physics, using arrows above the symbols, we show vector quantities. So thus, it has a weight, and the weight exerts pressure on the bottom area. So thus, suppose it, let me denote it by A from area. So let me begin with the what? The formula general for defining pressure, being force per unit area. However, in this case, which we are talking about hydrostatic pressure, it is the pressure due to the weight of the fluid column. So in this case, the fluid placed in that cylinder. So thus, force is weight divided by area. So thus, weight, we have just written, mass times acceleration of gravity. Also, having in mind the definition of density, mass is density times volume. Volume of the cylinder, let me by H denote its height. Then we can continue density, height, times area. This is volume. This one is volume.
What happens? You can't see. Tate varigu vikai. Oh man, that is pretty price. So, there were some technical problems due to the new system being installed here. That's why you and me both, all we have to be very patient. It is exceptionally stressful to me, frankly speaking, but what to do? So sorry for this line. I have just by to remove it a bit. And so that this is volume. And we've got G and A. So that's last time we discussed that area, if appears both in the numerator and the denominator, can be cancelled. And what is left here? It is density, then height, G. So that's hydrostatic pressure can be calculated via this product in which density of the liquid, height or depth, thickness of the liquid layer, or the height of the liquid column, and the acceleration of gravity. So let us consider some container, for example, let it be open one, and suppose the fluid being poured inside that container, and suppose it is filled to some depth or height, and let us ask a question. What is the pressure at some point, for example, point M, which is found at depth? So I'll remove that stroke here. So depth by h, let it be. And what is the pressure? So the question is pressure at point M, how to express. So initially, we need to take in mind the pressure exerted by the gas above the surface. By and by, it is called free surface of the liquid. And that pressure, due to the weight of the air column, is called atmospheric pressure. So let me put it here, atmospheric pressure exerted on the free surface. But which atmospheric pressure by and by it is exerted on the free surface, but is experienced by every point in the fluid according to the Pascal's principle. So thus at point M also atmospheric pressure is exerted. But there is one more pressure here, which is due to the weight of the layer above the level at which the point is located. So that layer has got mass, which means that it exerts weight, or a hydrostatic pressure. So thus, pressure at point M would be the sum of atmospheric pressure and the hydrostatic pressure. Or we can write P atmospheric plus rho G again H. I hope that it will quickly quickly start working since I have already written this. So here, what is written? It is written plus P atmospheric plus hydrostatic pressure, which is atmospheric plus rho G H. Dacă apoi tu că au pravis, au ne. Până să scriu. Da, scriu. Okay, so let's proceed further. We are following the text of the presentation. In the slide, it is given just hydrostatic pressure, but we also know how to express total pressure, sometimes called liquid pressure, or pressure at some point below the pre-surface of the liquid. Or sometimes liquid pressure, absolute pressure also is used to express this total pressure. So this picture is to conclude what? So there is a vessel which you see has complex shape, having different sections of different shape. The vessel is closed, which means that the liquid cannot leave it. And you see that irrespectively of the shape, the height is one and the same of that liquid, one and the same height, which tells us what? That the hydrostatic pressure is same irrespectively of the shape, and we know that. Since hydrostatic pressure is rho GH, so it depends only on the height, not on the shape. So the shape doesn't matter in case of hydrostatic pressure. So we've got here static liquid, liquid which is not in motion. This means static, not in motion. And if some small volume is considered within the fluid being placed in the cylindrical vessel, so that droplet or small volume is in equilibrium. So it behaves as if there are no forces being experienced. Here, in fact, there are forces, non-zero forces, but since pressure is exerted equally, which means that those forces are exerted equally from all possible directions and cancel each other, so that there's no net force. So we have to pay attention between net force, net. So that word is important in physics. Net. Once again, to switch on the board. And to write net force. That word net being also the meaning resultant. The net force is zero. So we've got non-zero forces, which suppose there is a single molecule being found in the center of this droplet, experiences forces from all possible directions, and they cancel each other, and we've got equilibrium situation. So further, we proceed with a demonstration, an experiment, showing what that hydrostatic pressure increases with depth. So, since we've got rho GH, if depth or height, depending on the situation, increases, so the hydrostatic pressure increases. So thus, let us consider the hydrostatic pressure at point A, B, C. So thus, horizontal flow being given here, trajectories of flow, since holes are punched in the wall, in the side of that vessel, and this shows that with the depth, pressure increases as judging by the horizontal flow and trajectory correspondingly. The pressure downward increases with depth in this very example. Application of the hydrostatic pressure in IV apparatus, which is used for vacuum fusion. What is given in the picture? The height determining the pressure which is exerted at the point of input, and that pressure, hydrostatic, does not depend on under static conditions, of course, on the configurations. Here is there coil turn, or just this is the height which determines, so between that part of the bottle which is in contact wear and the point of infusion in the vein. So AV apparatus being a demonstration of hydrostatic pressure application. So since I have already used Pascal's principle of Pascal's law, once again let us see it defined verbally. So any change of pressure in an enclosed fluid is transmitted equal or undiminished to all parts of the fluid. So many clinical applications of this Pascal's principle in medical practice, in everyday life, including, that's why some examples are given in the context of medicine. Firstly, chronically ill patients, for preventing the development of diffuse ulcers, they must use not ordinary, but matrices filled with some fluid, water or air. Why? Because, as given in the next slide, ulcers are produced as a result of bigger pressure exerted on parts of the body which have the smallest contact with the matrix, such as elbows, such as back, other locations, and if there is such a mattress, so those pressures which normally must be higher than surrounding due to the weight of the body, so they won't be different. So we will observe equal pressure exerted upon every part of the body due to the fact that there is a fluid which transmits pressure equally in all possible directions. So the same pressure is exerted against every part of the body according to the Pascal's principle. Another example of we are waiting this to start working. So to come back to the slide which we were discussing, this one. So that's another example of the application of Pascal's principle. It is an application
in the context of diagnostic of tumors. So there is a fluid, cerebrospinal fluid is the name, which circulates as given here around the spinal cord and tap into the subarachnoid space around the lower part of the brain. And if there is some tumor, it will occupy some volume of that space normally filled with cerebrospinal fluid, which will decrease the volume. And you know that there is a law, ideal gas law, and since gases are fluids, also liquids with some approximations can be explained using this very law. So let me just write it. Universal gas law, which is product between pressure and volume, stays same. We even know what is the right-hand side, number of moles, universal gas constant, and Kelvin temperature. So all they being constant under specific conditions. So thus we can shortly write this as PV is constant, fixed, which means that if the volume is decreased due to what? To the tumor, the volume being occupied by the cerebrospinal fluid is decreased. For the product to stay same, the pressure must increase. So thus the pressure of this liquid will increase in case of such a tumor, and there is a convenient location in which that pressure can be measured, and any increase in pressure may indicate and be used to diagnose tumor growth in that space. Another application, both features being protected by the external forces via fluid in the amniotic sac surrounding it, but at the same time, if there is some blow or some force being exerted on the abdominal area, through that fluid it will be transmitted to the fetus and may produce injury. And another application, the same for the eye, which contains enclosed fluid, and any blow to the front of the eye will be transmitted to the back by we will study the structure of the human eye out here in that course. And we will know more about the structure and image formation. But in this case, we should know that the force will be transmitted to the back, particularly optical nerves, blood vessels, retina, all they be delicate structures and can be easily damaged. Another example, normally in pericardial and pleural cavities, there's no collected fluid. But as a result of some disturbance, such fluid may appear, may fill those cavities, and heart as well as lung, they will be subjected to extra pressure or force due to the existence of that fluid, which transmits pressure due to the heart functioning, for example, and lung as well. So those were some applications of the Pascal's law, and now let us proceed with a phenomenon which is called buoyancy. Buoyancy is a phenomenon which is observed when a solid object is submerged in a fluid, solid object being submerged. And of about 300 years BC,
Greek philosopher, Archimedes, was clever enough to explain that phenomena, and there is a formula for the force being exerted as a result of the phenomenon of buoyancy on any submerged object, which is termed Archimedes force, buoyant force or Archimedes force. So since it is not given here, I'm going to explain before proceeding with the medical applications of the phenomena. So, buoyancy. Let me clear everything and consider some container, suppose, okay, I'm continuing and then you'll see everything. Hope that this will quickly, so let me try to see if I change the screens now. Just to wait a bit. And while waiting, I'm going to take a cube, since it has got a regular shape, and let me consider it being submerged in that liquid. So that cube, so let us focus on the top and bottom side. Both sides, they are subjected to the effect of hydrostatic pressure, but it is not same different is that pressure being experienced by the bottom and top height. Why? Do you know why? I think that you must have already known. Because those sides, they are located at different depth. Let me denote it via H1 and H2 according to the free surface. And the hydrostatic pressure being experienced by the bottom side, let me term it pH2, is, what is it? Rho GH2. Hydrostatic pressure being experienced by the top side is rho GH1. Which pressure is bigger? Of course, pH2 is bigger. Because H2 is bigger than H1. This is one here. So there is pressure difference. That's why that cube cannot stay here. It will experience a net force. A net force produced by what? By that pressure difference. So thus, let me write the pressure difference. pH, symbol delta, means change in. Change in, this is the meaning of the symbol. Change, this is H, please. Not easy to write. Here, delta pH is what? pH2 minus pH1. Also, we may term this delta pH net pressure being exerted on the cube. So that's why let us write once again the general formula for the pressure, and let us adjust the formula for the situation being considered. So thus we've got delta PH being force. Let us term it Archimedes force or buoyant force per area. What is this area? Cube side area. This is the area. So from here, we can express FA being delta pH, but it is pH2, which is this one, minus this. So thus I can write, let us, pH, delta pH multiplied by A. Delta pH is rho G H2 minus H1. A. What is H2 minus H1? It will be this H, which is the height of the body, in this case, the length of the side of the cube. So that's just H. We can write here. So that's we've got here H multiplied by area. What is this? This is the volume of the cube. If the bottom area is multiplied by the height, this is the volume. So thus we can continue. I will write below. FA is rho G and then volume of the cube. But at the same time, it is the volume of the fluid being displaced by the cube. They are same. So thus, Archimedes force is, what is this rho? Density. Density of what? Of, not of the cube, of the fluid, of water or whatever is there being a fluid. So thus, density of the fluid times the volume of the fluid being displaced, which is the same as the volume of the cube. So thus rho V is the mass of the fluid being displaced. I even may write here subscript FL from the fluid G, which is weight. As you know, weight is mass times acceleration, weight of the fluid being displaced. So thus, we can define in this way buoyancy phenomena, also Archimedes force or buoyant force. What is buoyant force? Buoyant force is equal to the weight of the fluid being displaced by the submerged object. So weight of the fluid displaced. And as we have already discussed, we've got pH2 being bigger than pH1. So we've got motion from high to low pressure, which means that the force Archimedes is directed upward. So we've got a weight of what? Of the cube and Archimedes force directed in opposite direction. So, and what would be the behavior of the cube depends on the magnitude of those two forces. If, I'm going to write here, if those two forces are same, the cube will stay motionless within the fluid. If weight is bigger, then the cube will sink. So moving downward and sink, and then resting on the bottom. If Archimedes force is bigger, it will float. And this explains the the ability of ships and other objects to flow on the water surfaces. So, and what makes the magnitude of those two forces? So let me clear some part and write here. So we've got a weight of the object versus Archimedes force. So weight of the object is mass of the cube of the object. Any object can be times acceleration of gravity. Archimedes force is what? Mass of the fluid times acceleration of gravity. So mass of the object is density of the object, its volume. Mass of the fluid is density of the fluid times what? The volume displaced, but volume is same. So thus even we can cancel them. So thus the behavior depends on what? On the difference between the density of the object and the fluid. This is if the body's density is bigger, it will sink. If it is less than the fluid density, it will rise and will float. So we will come presently here back, but let me switch on the presentation to see, and using exactly what I have just explained, explain the mode perfection of a device which is called graviometer, which is used in clinical laboratory, which is used to measure the so-called specific gravity or relative density of liquids. It can be plasma, it can be different urine, different biological liquids. So thus, specific gravity, also known as relative density, specific gravity or relative density. Let me clear this. And I write it as specific gravity or relative, R from relative density. This is density of the object and the density of the fluid being considered. Specific gravity or relative density. Dimensionless quantity. Let us see the picture now. What is given here? We've got some vessel cylindrical in which the fluid to be studied or liquid to be studied is to be measured, and there is some reference object always being used, which has got specific mass and density, which is put inside the vessel, and it will float. But how much it will float, it depends on what? On the density of the liquid being placed in the vessel. So thus, having in mind our explanation here, so thus, if the density of the body being submerged, but it is fixed. If the density of the fluid is changed, in this case it is fixed. If the density of the fluid is changed, suppose it is increased, the density is increased, what does it mean? That Archimedes force will increase and it will move higher, it will rise. And you see in in the picture there is a scale directly to take the values for the specific gravity. Since the composition of the biological fluid determines density, and when under specific conditions, for example, in case of urine, it is given that some diseases alter that composition, density changes, and the Archimedes force, consequently, the position of the body with respect to the surface here, free surface, would change. So thus, urinometers, they measure specific gravity or relative density, which shows or is an indicator of what? It is an indicator of the density of the biological liquid being studied. Density of the liquid being studied. So let me proceed further. Again, not working. Not ready to start working. Okay. So, in this slide, what is given here, another application of Archimedes force and buoyancy phenomena, which is used to measure density of irregularly shaped objects. In this way, we can find the average density of the human body. So verbally, but we're going to write it mathematically. The difference between the weight of an object in air and its weight when submerged in water is the buoyant force, which is equal to the weight of what is displaced. So let me try to explain. To switch on the board to clear everything. And let us take some object in air. So suppose this is its weight, of the weight of the object in air. I can write here air. Then let us put it in a container with some water, for example, or any fluid. So let us put it here. So thus we've got weight in air, and it will experience also when submerged Archimedes force, which means that its weight in water would be less. Why? Because when weight in water, so the weight would be weight in air minus Archimedes force. Since the weight is reduced by the Archimedes force, since it is directed upward, and when it is measured under water, not its pure weight is given, but the weight diminished by the Archimedes force. So thus we can rearrange this. So the weight of the object in air minus its weight in water would be exactly equal to the Archimedes force. So thus, in this way, Archimedes force can be found and calculated. And this formula is used, as I've told you, to find the density, for example, not just Archimedes force, since we know that Archimedes force depends on the density of the fluid, but weight of the object on the density of that object. So the average density, for example, of the human body, you've got such a problem in your practice book after the topic. So thus, in the rectangle in which we read, it was given exactly this: the difference between the weight of an object in air minus its weight when being submerged in water is equal to the Archimedes force. That is equal to the weight of the fluid displaced by the object. So this is what I have written mathematically. So in this rectangle, Google explanation of the formula WR minus W. W is Archimedes force. And as I told you, the main application of this is to find the density of volume. They are related by, as you know, the definition of the volume. Mass per volume is density, irregularly shaped object. So thus, up to this moment, we discussed fluid statics. And we studied what is pressure, different kinds of pressure, Pascal's principle, Archimedes principle, and different applications. Pascal's principle, clinical, and Archimedes force and buoyancy as well, in case of urinometer, for example. And now fluid dynamics, which means what? Fluids in motion. Fluids in motion. So what is given in the slide? Two pictures. So we've got vessel. In this case, liquid inside cannot leave it. But in this case, that part is open and the liquid can flow, which shows the main difference in what? In pressure. So in this case, the height is same in every part. The pressure is same. In this case, however, we see that pressure changes over the distance. So there is the so-called pressure gradient. So now we have to introduce an exceptionally important term. Since gradient we will use very frequently, not just in this course, but also in biophysics. For that purpose, let me write the term gradient. Gradient. We've got gradient. What is gradient? It is in space. Change of a quantity per unit length. Change in a quantity per unit length. This is gradient. And in the specific example, we've got pressure gradient, pressure per unit length. But we may have velocity gradient, as found in Newton's law. We may have concentration gradient, density gradient. Oh, this gradient can be introduced from any quantity if we consider in what way it changes over distance, then we can talk about gradient. So pressure per unit length is pressure gradient. Pressure gradient. Velocity gradient is the change in velocity per unit length.
Concentration gradient, the change in concentration per unit length or distance, actually for it doesn't matter, and so on. So gradients, change over distance. Why are we introducing this term gradient? Because we want to study fluid flow, especially they flow through tubes. And this we study to explain next time circulation, since blood flows through vessels which resemble or are modeled by tubes. There is a law which is called Bozoi's law. Bozoi's law, which determines volume flow rate. Volume flow rate. So pay attention, this F is not force. So in physics, we may use one and the same symbols to different things. So there are many examples you'll see in the course. So this F is volume flow rate, and it is defined as I'm going to write it for distinguish it from force. So in this way, this F being, but it doesn't matter, you may use any F. Volume flow rate, volume of liquid or fluid which is transferred or which flows through a tube per unit time. Volume per unit time. This is volume flow rate. By and by, another term, rate. Rate which is different from gradient. We've got a rate which shows if this is change over distance, gradient, this is change over time. So thus, if a quantity changes over time, we say the rate of change. If it changes over distance, we talk about gradient. So thus, rate is change over time. And we've got volume flow rate. And let me write the law, but in detail, and then we will write that short variant of it as given in the slide. So volume flow rate, when fluid flows through a tube, so we can introduce a quantity being called volume flow rate, which is defined in this way: pi r power 4 delta p, over h L. So you will presently see it, not now, just some time is needed, so that how much volume flows per unit time, as you see in the law, depends on the radius of the tube, on the length of the tube, on the pressure gradient, which is the driving force, which is the force which makes the fluid moving through the tube, and viscosity of the fluid. So much time now. To change slides to see will be any difference. Not yet. So while waiting,
At last. Okay. So this is what I have written. So we've got radius power 4. So delta P is what? The change in pressure between the two ends of the tube, across the tube, we say. It is Greek letter for dynamic viscosity, and L is the length of the tube. So thus, see here, delta P divided by L, this is what? Change in pressure per distance, which is pressure gradient. As I've told you, the volume flow rate depends on the pressure gradient. And let us introduce the so-called resistance to flow. I'm going to use the symbol R, and let it be the denominator over pi R power 4. So then this formula can be shortly written as delta P over R, or as given, you can see in the slide, we've got the difference between upstream and downstream end of the tube and resistance to flow. You can see here in verbal way. Resistance to flow. So thus P, it doesn't matter 1 or 2, you'll decide it, but it must be bigger pressure upstream minus downstream pressure. So this formula is called, as we have already stated, and it shows that the volume flow rate is proportional to the pressure gradient, with the coefficient of proportionality being the resistance to flow reciprocal value. Let us, so this formula we will use very much frequently throughout the course, but not only in the biophysics as well, since that formula used to explain osmosis and filtration through pores in cellular membranes of water, for example, or other biological liquids. So that's law which we'll frequently use. So, yes, as the fluid flows through the tube, pressure decreases. We saw this in the picture. This one, pressure decreases. And what is the reason for this decrease in pressure? Losses in energy. This is the reason. And since I saw here drops in pressure. So if pressure decreases, then instead of say pressure decreases, we might say pressure drops. It is 100%. Or how to mathematically write pressure drop? Delta. This is pressure drop. Decrease in pressure. And those losses of energy is due to what? The fact that fluids are real and they experience friction. Frictional forces oppose motion and retard. And some losses of energy is observed. And again, we can't, they continue, and I suggest you some break
entrance.